Let's say I have a fair 6-sided dice, and after rolling it 10 times, I get the number 5 8 times. Now, I'm curious because that seems pretty unlikely, but I can't be totally sure because it could have happened by chance. But what I can do is conduct a hypothesis test and see if there's been some sort of change in the probability P of getting a single 5. Now, this is actually quite a hard chapter, hypothesis testing, but I'll try and explain it in a way that makes sense and so that you can understand why I'm doing all of the steps. So usually the probability of getting a 5 is 1/6. So we can make a null hypothesis, or H0, that says the exact same thing. P is equal to 1/6. So this null hypothesis is a starting assumption that says there's been no change to the probability P. We can also make an alternative hypothesis, H1, which says, and in this case, since we got 8 5s, that seems like something you'd get if the probability increased. So we can say that probability P is more than 1/6. So in this case, H1, or the alternative hypothesis, is an assumption that there's been an increase in the probability. So both of these are predictions about the scenario we're looking at. After the test, we'll be able to reject one of them. Now, since rolling a dice for the number 5 has 2 outcomes, either getting a 5 or not getting a 5, and each roll is independent, we can model this with a binomial distribution. So let's say x is distributed binomially with the number of trials 10 and the probability of success 1/6, where in this case x is equal to the number of 5s that we roll. Now, what I need to do is see what the probability is of getting x or anything more than 8 or anything more than 8. Now, why have I chosen 8? Because we got 8 5s, and I want to see if we get anything more than or equal to 8 and what the probability would be of that. Why did I choose more than? Well, since I'm looking to see if the probability is increased, an increase in probability suggests that you get more 5s than what one would normally expect, somewhere around 2 or 3. Now, I want to find anything that's more than or equal to 8 because that will suggest an increase in the probability. So before we do the actual test, I'm going to mention something about this probability here. Sometimes questions will refer to this as the p-value. So the p-value literally just means this probability of the extreme case of our scenario we're looking at. So in this case, the extreme case would be getting anything more than or equal to 8 5s. So that is our p-value. Now, for simplicity, I'm going to refer to this as the p-value from now on, and p by itself just means the probability of getting a single 5. Now, what we need to do next is compare the p-value to a significance level. So significance level basically tells us how low the p-value has to be in order for our result to be significant and suggest there's been some change to our original assumption. So usually in questions, there'll be a 5% significance level, or 0.05. And in some questions, they might give you a different significance level, 1%, 10%, but if there hasn't been anything given, it will always be 5%. Now we compare our p-value to the significance level. So px is more than or equal to 8 is equal to 0.00002. Clearly, that's less than 0.05. Now, the next step is to analyze this in context, and this is one of the most important steps in the hypothesis test. So we can see that our p-value is less than our significance level. What that tells us is that our result is significant. Now, since our result is significant, that's telling us that assuming the probability P was 1/6 for getting a single 5, assuming that this event happening where we get more than or equal to 8 5s is very unlikely to have happened by chance with the probability of getting a single 5 equal to 1/6, which means that it's very unlikely this happened assuming that was true, which means that we reject the null hypothesis because it's very unlikely that was true. So we say that because of this test, there was sufficient evidence to reject the null hypothesis, or to reject H0. And then we put into context. So in the context of the question, we were trying to see if the probability increased. So there's sufficient evidence to reject H0 and suggest the probability of getting a single 5 has increased. and that is our hypothesis test. So this was a one-tailed test, which is basically testing for one extreme tail, in this case looking at anything more than or equal to 8, so on one side of the extreme, but you can also look to see for the probability on both sides, on both extremes, and that would be a two-tailed test. For now we're going to stick to just one-tailed, and in the next video I will go through two-tailed tests. But now what I'm going to do is give you a couple of examples to try yourself, and then we'll go through them together and see how to approach them in an exam style way. So here we've got an example question, and we've been told that 30% of restaurant customers ordered starters, and in a sample of 40 of them, 7 of them ordered starters. We need to test at the 5% level if the proportion has decreased of people who are ordering starters. So have a go at this yourself and pause the video, and then we'll go through it. Okay, so first we need to see what our null hypothesis is going to be. So H0 is going to be P is equal to 0.3. This is assuming no change to the original probability of 30%. Okay, now our alternative hypothesis is going to be P is less than 0.3, because we're trying to test and see if the proportion has decreased, which means that probability P would be less than what it was originally. Now our binomial distribution is going to be x distributed binomially with the number of trials 40 and probability of success 0.3. Now it's binomial again because you can either order a starter or not order a starter. And in this case, x is equal to number of people ordering starters. Now the next step is to find out what probability we're going to calculate for our p-value. So we want to find a probability P of x is less than or equal to 7. Now why do we choose this? Because we had 7 people ordering starters, so I want to find the probability of the extreme case where we order 7, or we have 7 or less people ordering starters, because if the probability is decreased, that would suggest we get less and less and less people ordering starters. So this is our extreme case that we would have to find, assuming that the probability was unchanged. And this would then be our extreme case. So we find this probability, so you just plug it into your calculator. So I've already put it in, so you have binomial CD, x is equal to 7, n is 40, and p is 0.3. So we get probability of 0.05528. So this is equal to 0.05528, and now we compare this to our significance level of 5%. So 0.05528 is more than 0.05, and we can see here that our p-value is more than the significance level. This tells us that the result was not significant. So result not significant. Now because the result was not significant, that basically tells us the p-value was high enough of a likelihood to have happened, assuming the probability was 0.3 of ordering a starter. So we don't have enough evidence to say that it's actually decreased. So now we just say that. So insufficient evidence to reject the null hypothesis, H0, and suggest the proportion of people ordering starters has decreased. And that's our hypothesis test. So here's our next question. It says the chance of getting a 3 on a fair spinner is equal to a quarter. Now Alex thinks that the spin is not fair and the probability of getting a 3 is greater than 1/4. She spins it 40 times and gets the number 3 15 times. And the first part of the question wants us to state our hypotheses clearly. So pause the video and try and write those out yourself. So writing out the hypotheses, we start with H0, assuming no change, so P is equal to 1/4. Then the alternative hypothesis H1, since we're trying to see if the probability of a 3 is greater than 1/4, we just write that down, P is more than 1/4. So those are our hypotheses. Now to do the actual test, we now need to find the probability that, so we need to find the probability of getting 15 or more 3s, because a probability higher than 1/4 would suggest getting more 3s than what we would expect. So first we make our distribution. So x is distributed binomially with trials 40 and probability of success 1/4, where x is equal to the number of 3s. Now we want to find p. X is more than or equal to 15, again following the same sign as our alternative hypothesis, and then we calculate this. So let's go to binomial CD. So x is equal to 15, n is 40 still, and p is now going to be 0.25. So our probability ends up being 0.973. Okay, so I've actually made a mistake here. We're doing x is more than or equal to 15, which means that we need to do 1 minus px is less than or equal to 14. Now, if you have a graphing calculator, you can actually just do this yourself. But if you've got the calculator that looks like this, then you won't be able to do that. So you actually need to find the probability of 14, and that's equal to 0.94. So this is equal to this is equal to 1 minus 0.9456 to 4 decimal places, and that is equal to 0.0544. Now, our significance level for this test is 5%. So we will say 0.0544 is more than 0.05. So that means the test is not, the result is not significant. And again, that means there's insufficient evidence to reject H0 and suggest the probability of 3 has increased. And that is our test. So here are some exam tips to keep in mind just to finish off the video. So for one-tailed tests, when doing px is less than or equal to a certain number or more than or equal to a certain number, the sign will always be the same as in the the alternative hypothesis. So for example, if your alternative hypothesis is p is more than 0.7, then you'll do p of x is more than or equal to the number. And this number small x will always be the same as the number of successes they told you about in the question. So for example, if it's like a sample of 40 and you got, say, 7 people winning something, then you put 7 into your x. So if you don't have a graphing calculator when you're doing probability of more than or equal to that number, you always do 1 minus probability x is less than or equal to that number minus 1. So for example, if you want to find the probability x is less than or equal, more than or equal to 15, you do 1 minus p x is less than or equal to 14. This is only if you don't have a graphing calculator. If you do, then you can just plug this straight into it. When you're doing your test, you either reject H0 or you fail to reject H0. You do not reject H1. That wouldn't be correct terminology, so it's always dependent on H0. When you're analyzing your result, you always say that the test result is either significant or it's not significant. And with that, you then say there's sufficient or insufficient evidence to reject H0, and then you put it in the context of the question. So whatever the context was, probability increasing or decreasing, you say there's sufficient evidence or insufficient evidence to suggest that.